Okay, hi everyone. We are going to jump right back into integer arithmetic part 2, continuing along the same themes of proving / recalling all the basic facts about integers that we're going to need in the course. So our next little topic here is going to be the division with remainder, also called Euclid's division algorithm. Euclid's division algorithm. So again, like a lot of these facts, goes back to good old Euclid, although certainly it was known for thousands of years before that. So what is Euclidean division? So it's the question of what happens when you try to divide one number into another, and what do you? Of course, we're talking about natural numbers and integers, and so of course you can't always do the division exactly, but you can get some remainder. So the theorem reads as follows, the modern statement of the theorem. Let a be any integer, and let d be strictly greater than 1. D is also an integer. I could have said d and n, of course, because it's bigger than 1. So you're trying to divide. So d is the thing that you're dividing into a. And so then the claim is there exists q in z. So q stands for quotient, and r. I should clarify, r is also in z. I should just keep putting in z, but I'm not. Here we go. There exists q in z, r in z, and here r is supposed to be between 0 and d, right? So, d is a natural number 2 or greater. So r is a natural, or excuse me, 0 or a natural number less than d. So that a equals q times d plus r, right? So in other words, you try to divide d into a, and sometimes you succeed and the remainder is 0 and you get a is something times d, right? But other times you fail and you're left over with something. And the theorem just says that that's something that can be chosen to be small compared to d. Okay, so this is intuitively, I think, completely clear. We'll prove it in a moment. Also, let me note that given a and d fixed, q and r are unique. So q and r, this q and r are unique, right? So for a given a and d. So given that we have an integer a and a natural number d, you always get such a q and r, and there aren't two such pairs. There's only one. All right. So this is just elementary school division. You try to divide one number by another. Sometimes you nail it on the head. Sometimes you get a remainder. The remainder is always less than the number you tried to divide by. Okay, so nothing shocking there. But since we're in a big kid math class, let's actually give a proof of this fact. So the proof is going to proceed by induction. So we're going to start with a greater than or equals 0, and we're going to do induction, and then we'll flip and do negative a at the end. So we start with the case a greater than or equal to 0. Okay, so of course, so d is a natural number, and now we're saying a is 0 or greater. So in fact, if a, usually the base case would be a is 0, but in fact, I can take a less than or equal to, or excuse me, a less than d itself as a base case, because if a is such that a is less than d, then of course I can't divide d into it except by multiplying d by 0, right? So then then a equals qd plus r, where q is 0 and r is a. Right? If a is greater than or equals 0, but less than d, then right, our conditions on the remainder is that R is greater than or equal 0, but less than D. So A just is the remainder. Q is 0, and A just is the remainder, right? So the base case of our induction actually includes A, 1, 2, all the way up to D minus 1. We can just do them all simultaneously. They all work in a direct way. Okay, and so now we'll assume that the theorem is known. So now we'll use strong induction. So assume that the theorem is known for all B less than A, and we prove it for A. Which we can take to be greater than or equal to D, because the base case covered all cases where A was less than D, right? So you assume A is greater than or equal to D, and you assume that the theorem is known for all, instead of A, you put B less than A, right? And that's exactly what we did in the base case. If A is D, right, the kind of first case of this would be if A is D, and then we just proved it for all A less than D. Okay, so A is greater than or equal D. So since A is greater than or equal to D, that means that A minus D is greater than or equal to 0. Let's call that B. So the theorem is known for B. So by induction, by strong induction, the theorem is known for B. We have B equals Q prime D plus R, right? We can do the division. We can divide D into B and get this, where R is in the correct range, and Q prime is some number. I don't know what Q prime is, natural number in this case, but yeah, right? Something that whatever you get when you do the division, which is known inductively for this number B, right? Okay, so this equation is saying, so therefore we have A minus D equals Q prime D plus R, and that's saying that A is Q prime plus 1D plus R. And so there's the existence of Q and R, right? So this is what we're going to now call Q, and that's A is QD plus R. So that's the existence of the division. I haven't gotten uniqueness yet. I'll do it at the end. That's the existence of the division algorithm for all A greater than or equal to 0. So now suppose A is less than 0. Okay. So by the previous part, we can do the thing for minus A, right? So we know from the above, the previous part of the proof, that I can do division for minus A. So that minus A, which is now positive number, is equal Q, and let's call it Q tilde D plus R. For now, Q tilde some integer. Now it will be a negative number, and R is in the range that we like. Okay. So of course I can minus this whole equation, and I can get that A is minus Q tilde D minus R. So we haven't quite won yet, right? Because this, I want something times D plus a little natural number, and now I'm taking something times D minus a little natural number. Okay, but because of the range of R, you see minus R, see R is between 0 and D, excuse me. So minus R is between minus D and 0, right? So we have minus D less than minus R less than or equal to 0, right? Now that's just exactly the same equation as 0 less than or equal R less than or equal D. I've just minused it and reversed the orders as we must do. But it's useful to do that because this equation tells me, right, that if instead of working with minus R, I work with D minus R, then I'm in a good range again, right? Or rather, I had better work with yeah. Well, no, D minus R is okay. I guess I'll say it this way. Okay, let me say it. I'll break it into two cases to say it the most convenient way. So if R equals 0, then we're done. Then we're done, right? Then A equals minus Q tilde D, and that's it. We've done the division algorithm because A has been divided by D. It's equal to something times D plus 0, right? Minus 0 is equal plus 0. So this is in the form that you need for the algorithm. If R is not equal 0, then I'm going to do this. I'm going to write A is minus Q tilde times D minus D plus D minus R, right? So now this can more conveniently be written minus Q prime minus 1 D plus D minus R. Now, where does D minus R live? D minus R lives between, let's look at the top equation. We have minus D less than minus R less than or equal 0. So that's 0 less than D minus R less than or equal to D. And because we assumed that that R was not 0, we certainly don't have the right-hand inequality. Right? There's no way that we have, right? If D minus R would only be D when R itself was 0, right? So we have a strict inequality there. We have 0 less than D minus R is less than not equal D. And so D minus R is a perfectly good remainder for this equation. And so this equation, this equation satisfies the conditions. So we have A equals QD plus R prime, where this Q was minus Q tilde minus 1, and this R prime was D minus R, and this is of the form that we wanted, right? This is exactly the claimed thing. We have some integer times D plus something, and that something is in the correct range of, that something is in the correct range where it should be, between 0 and okay. So in all cases, we see that the division exists. Kind of a long-winded proof, but the idea I think is obvious. And now finally, let's go for the uniqueness part. Uniqueness, suppose you have two different decompositions. So suppose QD plus R is equal Q prime D plus R prime, where now Q prime live in Z, and R prime satisfy the bound. That's a sloppy way of writing that. R and R prime satisfy the bound, like that. Okay, so suppose those things are true, then of course these two equations together, they can be rearranged, and they can give you that Q minus Q prime D is equal to R prime minus R, right? So I subtract off the R from there, I subtract off that from there. Okay, now what is this R prime minus R? It's the difference between two things that are between 0 and D, okay? So let's take their absolute value. So, you know, how big or how small can it be? It can't be bigger than D, right? Because it's at, if I have one extreme, I would have D minus 0. And it can't also be less than minus D, right? I could have 0 minus D. Those are the two extremes, right? So in absolute value, it's strictly, it's strictly less than D, because at the biggest it could be is D minus 1 and 0, or 0 and D minus 1. So we have that the absolute value of R prime minus R is less than D, right? And that's just a basic fact, just comparing the sizes of any two different numbers that are between 0 and D minus 1. The extreme difference is 0 to D minus 1 itself. So absolute value of Q minus Q prime times absolute value of D is equal absolute value of R prime minus R is less than D. But that's a problem, because now we're saying that some natural number times D is less than D. So that only makes sense if Q minus Q prime is 0. So this implies, right, you just stare at that equation for a second. This clearly implies that Q minus Q prime, well, absolute value of Q minus Q prime is 0, which is the same as saying that Q equals Q prime, right? And once Q equals Q prime, then if you look at the original equation, QD and Q prime D cancel, and so R equals R, right? So this immediately implies that R equals R prime, and we've got it, okay? Okay, so, all right, so that's the Euclid division algorithm, Euclidean division. If you look in the notes or in the book, there are some worked examples of how to actually perform it. You can review those at your leisure. But it's the familiar concepts from elementary school. There's nothing fundamentally, nothing new has happened in this field in 1,000 years or something. So there's not, I'm not going to try to convince you that that there's something new to learn. You got, it's the same thing you guys learned as kids. Okay, so the next concept that we want to talk about, and the one whose proof uses the Euclidean algorithm in a crucial way, is the greatest common divisor. So let's talk about the GCD, the very important concept in basic arithmetic, the greatest common divisor of two natural numbers. So you can do the GCD of two integers. Yeah, in fact, I think we will do it. It looks like we, in this course, our convention is that m and n can be any two, or I'm going to call them a and b. No, I'll follow the same notation as the notes, that m and n can be any two integers. Yeah, okay. So let's do it this way. So let m and n in z, then d in n is, I could say a GCD, but I'll just say the GCD, and that'll be justified momentarily, is the GCD, and that stands for greatest common divisor. Of m and n if 1, well, D is a common divisor. In other words, it divides both of them. D divides m and D divides n. So that's the first thing to do. And 2, greatest, right? It's supposed to be the biggest possible common divisor, but there's more. So if x, yeah, okay, I can even do this for x and z. So if x in z is such that x divides m and x divides n, then x divides d. Okay, so it's great. So it's not only is it, okay, so let me remark, if d exists, and it always does, but we haven't proved it yet. I will get to that in a minute. If d exists, then clearly d is the maximum of the set of x in n such that x divides m and x divides n, right? Because if you look at that set, anything in that, any elements of that set is not empty, by the way, because 1 is in it. Whatever m and n are, 1 divides m and 1 divides n, and 1 is a natural number. So this is some non-empty set of natural numbers. It's out there, it exists. It's clearly bounded, right? It's a finite set because m and n are just integers. And so whatever is the bigger absolute value between m and n, nothing bigger than that can divide both m and n, right? Clearly. So it's a bounded finite set of natural numbers. So whatever it is, it has a biggest element, right? But now what these conditions 1 and 2 are saying is that any element of this set divides d. And so d is in the set, d is a natural number, d is divided by anything in the set. So clearly these all imply that d is the biggest element of the set, right? There's nothing bigger than d can divide d, just obviously. So this is some good non-empty set of natural numbers that you can attach to m and n, and it has a max, and that max must be equal to d. However, so d really is the greatest common divisor. It's the biggest natural number which commonly divides m and n. However, comma, this does not yet prove that d exists, right? There's something else to say because we haven't shown that for any other element which divides both m and n, or excuse me, yeah, for any other element which actually divides both m and n, it has to divide into d, right? I could always take this set, I could always take the biggest element of it, but why does every other element of it divide into it? It's not clear, right? It isn't, there's no obvious reason for that to be true. I mean, just staring at it seems plausible, right? But there's no obvious reason for it to be true. So we have to both, so we have to justify why this thing exists. This remark is only saying that if it exists, it deserves its name. It is the biggest common divisor. And furthermore, it's clearly unique, right? So in particular, the GCD of m and n is a unique thing because, Well, look, it's the biggest number amongst the set of common divisors. There's only one biggest number in a finite set. So therefore D is unique. So therefore GCD of Mn, if it exists, is unique. If it exists. Okay, so that's the first point to make. It really is the greatest common divisor. Okay, but let's not beat around the bush. The main theorem is that, in fact, it does exist. Okay. Before I state the theorem, let me give you a definite. Well, I'll state the theorem and then I'll give the definition. So theorem, for any M and N in Z, GCD Mn exists. Okay. Further, there exists some A, B in Z, so that the GCD of Mn is Am plus Bn. Okay, so not only does it exist, but it is a linear combination, right? So in linear algebra, we talk about linear combination, so I think I can use that language. It's a combination, a linear combination of M and N. In other words, it's some integer multiple of M plus some integer multiple of N. That may not seem that significant, but it's actually quite significant. We'll talk a lot about the meaning of that, and especially its consequences for modular arithmetic and other areas of algebra as we move forward. But just let me pause and suffice to say that this is a very significant fact that we will return to and use often. So you get the existence as well as some sort of deep fact about how the GCD is constructed. We'll prove them together when we prove this theorem. Okay, but before I do that, let me give you an important definition and just a quick concept of how this relates to prime numbers and other things. So if the GCD, so assuming the theorem, right? Let's assume it always exists. We'll prove it in a few minutes. If GCD of M and N is 1, then M and N are called relatively prime. Are called relatively prime. Okay. So let me just specify what this means in the important case, right? The word prime is coming up. So is this related to prime numbers? It is indeed. So if M equals P is prime, right? If M is a prime number, then GCD of P and N is 1 if and only if P does not divide N. Okay? So N is relatively prime to P. It just means that P isn't a divisor. Okay? Why is that true? So let me justify that, and then I'll talk about the notation a little bit. So this is because the GCD has to divide P. It's a natural number, it divides P. It's either 1 or P, right? So proof GCD of Pn divides P implies GCD of Pn equals either 1 or P, right? Those are the only two options. If it's P, this implies, since the GCD does divide N, this implies P divides N. GCD is 1, therefore implies P does not divide. Okay, so that's a justification for that statement. Okay, and so the GCD being 1 in the case of a prime, in the case one of the entries is prime, it means that P doesn't divide N. So that means that when you take N and break it up into its prime factors, this prime P doesn't appear. And that's why they're called relatively prime, right? Because it means that the primes of the one don't touch the primes of the other, right? So this is so we'll talk about more about this when we talk about give the proof of the second part, the uniqueness part of the prime factorization theorem. But let me just say that this kind of means that the primes that make up n don't include p. So sort of casually, this is saying that the primes, the prime factors of n don't include p. So I'll just write that in English without going into the details of uniqueness yet. We'll do that in a later lecture. So the prime factors of n do not include p. And that's the reason for the word relatively prime. Okay, so those are some important derivational concepts that come out of GCD. So now I'm going to return to the big theorem that the GCD of any two integers always exists, and in fact it can be characterized quite well, maybe not characterized simply, but in fact it can be constructed as a linear combination out of m and n. Okay, so let's prove the theorem. So proof of the theorem. Okay. So the first case I'm going to do, just to get it out of the way, is if either m or n is 0. So first, suppose either m or n is 0, or both. Or n is 0. Okay, so what's the GCD in this case? How do we do it? So yeah, so in this case, okay, everyone, tiny in video edit here. Sorry about that. So as I was starting to write the proof the case where they could be 0, I realized that it didn't make a lot of sense. And in fact, I looked at the notes again, and they certainly are both supposed to be non-zero. So sorry about that. So we're going to say z. So I went back to where the theorem is, and we're going to say let m and n be z minus 0. So when I put the notes up, that'll just be there. You could forget I wrote it any other way. And now let's return to the proof. So you should not suppose that either m or n is 0. The concept doesn't make any sense in that case, because the set of divisors won't be, 0 will be the only thing in the divisors. You won't have natural numbers anymore. So you should definitely take non-zero elements for GCD. So please re-edit your notes to reflect that. I'm sorry about that. Okay, so let's prove the correct version of the theorem. Let's prove the correct version. Let's suppose that you have two non-zero numbers m and n. So let m n in z minus 0 be fixed. And now what we're going to do is we're going to consider a certain set of natural numbers. So let's consider the set am plus bn, where a, b are in z, and the whole result, am plus bn, is in n, right? So we're going to consider all of the possible integer linear combinations of this m and n. And we're just going to look at all of them for now. All the ones that land in n. Are there always ones that land in n? Yes, there are, because, for instance, m is non-zero, so either plus m or minus m is a natural number. And then I can take b to be, so I can take a to be either plus or minus 1 and b to be 0, right? And so some integral linear combination of m and n certainly lands in the natural numbers. So this is a set. It's an interesting non-trivial set, and we can consider it. We can consider anything we like about it. Okay, and so we're gonna consider a particular element of this. We're gonna consider its minimum. So let d be the minimum of, let's call the set, I didn't give the set a name, let's call the set S, let's call the set SMN, and let D be the minimum of that set SMN. Now, let me pause here and to reflect the fact about natural numbers. This is an infinite set of natural numbers. It might not have a maximum, but it definitely has a minimum, right? And this is just a basic property of natural numbers. They're discrete, 1, 2, 3, 4. So any set of them has the smallest element, right? You can take 1, is it in your set? Yes or no. 2, is it in your set? Yes or no. You for each natural number, you can check, right? The set has some concrete definition. You can check whether it's in the set. You can return yes or no, and you can keep going until you hit a yes. Well, that's the minimum element of the set, right? That's kind of a concrete way of saying it. At any rate, it's an axiom called the minimum axiom for natural numbers. You can look it up. It's a basic set theoretic property of the natural numbers, but any set in the natural numbers always has a unique minimum element. Okay, so that's D. I am going to now show that D is the GCD of M and N. So we're going to write D. So we're going to write D is A tilde M plus B tilde N. And let's check that D is the GCD of M and N. Okay, so this is a good proof because it kills two birds with one stone. We're going to prove the GCD exists by checking that this number satisfies both axioms of GCD, and then we will instantly obtain the other interesting fact. Let me return it. Yeah, that the GCD is a linear combination, an integral linear combination of M and N. Why do we obtain it? Because D by definition is an integral linear combination of M and N, right? We took SMN, which was the set of natural numbers, which are integral linear combinations of M and N, and we just took some element of it, in particular its minimum, some distinguished element. And so the fact that D can be written as this combination is just instantaneous from the way that we prove that D exists. So that's why I said, in case you're wondering, that's why I stated the theorem that way, because you can do both at once. It's kind of a nice way of doing it, in my opinion. There are other proofs that GCD exists, you can look them up, but this is the one I'm going to do. I think it gives this useful property at once. So let's check that D is the GCD. So we have to check two axioms. The first axiom we have to check is that D divides both M and N. So we need to check D divides M, D divides N. The proof is identical for each one, so I'll just do it for M. So let's try to divide D into M. So by the Euclidean algorithm, by Euclid's algorithm, we can write M is QD plus R, where R is something that's between 0 and D. So this is where this minimum, if you guys are wondering, why did I say, where did minimum come from? Well, you're about to see. So M is QD plus R, where R is something between 0 and D. Now D, as we've said, is this combination, this A tilde M plus B tilde N, this funny combination of M and N. So this implies that M is Q times A tilde M plus B tilde N plus R. Okay, so simplifying that down again, I'm going to move everything over and solve for R. What do I get? I get 1 minus Q tilde A M plus minus QB, oh, sorry, the tilde was on the A, not the Q. Mistake. 1 minus QA tilde N plus minus QB tilde N is equal to R. Okay, arithmetic. But wait, we say, that is showing us that R can be expressed as an integral linear combination of M and N, right? So we conclude that, that if R was not 0, it would be in this SMN, right? It would be a combination, an integral linear combination of M and N. So if R was greater than 0, if it was a natural number, then this would imply that R is in SMN, and that is a contradiction. It contradicts the fact that D was the minimum. R less than D, I'll actually write it because it's an important point. R less than D contradicts the choice of D, right? So if R was greater than 0, you would have found a smaller element inside SMN than good old D. And that is a no-go because D was the minimum. So this contradiction proves that R can't be bigger than 0, right? So R equals 0, and what does a 0 remainder in your division mean? It means that D divides M, right? M is QD plus 0. And by the exact same argument with M swapped for N, D divides N as well. So in exactly the same way, literally no change in the proof, except for changing the names. D divides N. Okay, so we've got D divides M, and we've got D divides N, and that's the first piece of the puzzle. Now, part two, let X be in Z so that X divides M, X divides N. Then we need to check that X also divides into D. Okay, so let's write M is M1X, N is N1X. Okay, highly possible, right? I mean, what does it mean for one thing to divide another? It means exactly that you can do this. M is M1X, N is N1X, right? Okay. Now, what is D? Well, remember that D is the minimum of this integral linear combination thing. It's A tilde M plus B tilde N. So D is A tilde M plus B tilde N, which equals A tilde M1X plus B tilde N1X, which is A tilde M1 plus B tilde M1 times X, right? But that's just a big way of saying that X divides into D, right? If I divide M and I divide N, if I can peel out of both of those, then because this is a kind of combination of M and N, I can pull the X out and get that X divides D, right? So this is implying that X divides D. Okay. And that's the big theorem on GCDs, right? That's it. Because we've proved that D, this funny minimum D, satisfies the two crucial properties of the two definitional properties of a GCD. D divides M and D divides N. And for any other integer that divides into both M and N, that integer would divide D. And so as I remarked above, D being a natural number, right? It's a natural number which satisfies those. So it's exactly right. It comes from this SMN, which is a set of natural numbers. And so putting it together, you get that D is the biggest of the common divisors of M and N. And so it is the unique GCD. And so the GCD always exists. Okay. All right. Okay, so now that we've proved that the GCD exists, we're going to do a few corollaries of that, which are related to prime numbers and prime factorization. Okay, so let's talk about one of the first important corollaries that the GCD exists, which is a proposition, theorem, if you like. Our notes call it a proposition, and so I'll follow that. So proposition. In fact, I'm going to phrase it slightly differently. It's phrased as an if here, but it's actually an if and only if. So let P be a natural number, and let AB be non-zero integers. So Z integers in Z minus 0. Then P is prime if and only if, so the arrow goes in both directions. In fact, I'll write that out because this is important. If and only if the following is true, whenever P divides AB, then either P divides A or P divides B. So this property is an alternative characterization or alternative definition you'll even see in some contexts of what it means to be prime. Whenever P divides a product of integers, either P divides A or P divides B. So that's a property that a natural number can have. And I'm saying that the natural numbers that have that are precisely what we call prime numbers. Their only divisors are one of themselves. So the original definition of primeness we gave is about things dividing into P. This definition is P dividing into other stuff. So it seems like the opposite perspective, but nonetheless, it's going to yield the same. It's going to yield the same notion. Okay, so this is a very, very important fact in elementary arithmetic. So let's prove it. So we're going to prove the the forward direction if P is prime. So let P be prime. Okay. Now suppose that P divides AB. We want to show that if it doesn't divide one, it doesn't divide the other one. So suppose that P divides some AB. Suppose P divides AB and that P does not divide A. So suppose P doesn't divide A, we have to show that then it does divide B. It worked the same way. If P didn't divide B, we'd have to show it doesn't divide A, but I'll just pick one. So suppose P divides AB and P doesn't divide A. Okay, so since P is prime, what does it mean for P not to divide A? Well, P does not divide A precisely means that the GCD of A and P is 1, right? P is prime. Its only divisors, as we talked about before in this lecture, its only divisors are 1 in itself. So you either divide a number or your GCD with it is 1. So here we're using the fact that the GCD exists, right? So I'm not using any super hard thing about GCD. I'm just using the basic fact about GCD of prime numbers, and of course the fact that the GCD of any pair of numbers exists. Okay, but what do you know about GCD? We know that it's constructed as an integral linear combination of the two things, right? So GCD AP is 1 implies that 1 is equal to, let's call it XA plus YP for some X, Y, and Z. I don't know what they are, but they exist by the way that I proved by my theorem before, proving that the GCD exists, right? So there's some integers such that this is true. Okay, so this is an equation for 1, but equations for 1 are very good because I can multiply them by anything and get an equation for that thing, right? So that implies that B is BXA plus BYP. So we have an equation for B, and I'm just going to slightly rewrite this as XAB plus BYP. Okay, but P divides AB, and P divides, P. So if AB itself is P times, I don't know, L, then rewriting the equation again, we get B is X LP plus BYP, which now I'm really belaboring the point, but why not, is XL plus BYP. And so that implies that P divides B. Right? So if P divides the product AB and it didn't divide A, then you could force it to divide B. And of course, by exactly the same mechanism, if it didn't divide B, you could force it to divide A. And so it satisfies the property. Whenever P divides AB, then either P divides A or P divides B. Okay, let's go the other way. Let's suppose that P satisfies this property. So now suppose, what did I call it? Bullet point? What did I say? Oh yeah, bullet point. So bullet point number 2, which is also a bullet point. Suppose that you have the property. So suppose P and N satisfies the property that whenever P divides AB, either P divides A or P divides B. Okay? All right. So we want to show that P is prime. Okay? So how do you show something is prime? You try to check whether something else divides into it. So suppose P satisfies this property. So can we write, suppose we can write, I guess we'll go by contradiction technically. Suppose we can write P is equal X times Y. So suppose that you can factor P out into 2 other factors, X, Y, and N. Right? Suppose I can find some natural numbers that factor out P. Well, if P equals XY, then P divides XY. So this implies that P divides XY, and this implies that either P divides X or P divides Y. Okay, but X and Y are natural numbers that divide P. So if let's say it's X, if X divides P and P divides X, XP in N, right? We proved in the previous lecture that if x divides p and p divides x, then x is plus or minus p. Since x and p and n, they're both positive, and so that means that x equals p. Then x equals p, so y equals 1, right? So if p is xy, then one of the two factors is p and the other one is 1, and that's saying that p is prime by our usual definition. There's no non-trivial divisors of p other than p itself and 1, right? So p is prime according to the other definition. So p is prime according to the original definition of prime, and we've got our if and only if. If p is prime, it satisfies this funny dividing into condition, and conversely, any natural numbers that satisfies that condition certainly must be prime. Okay, so that's the first corollary. The next corollary is the second part of the theorem, the famous fundamental theorem of arithmetic that we've been talking about, the fact that the prime factorization is unique. So the second thing is you can call it theorem, you can call it corollary. I'll just call it theorem, and I'll call it FTOA, fundamental theorem of arithmetic, part 2. Okay, so fundamental theorem of arithmetic, part 2. How does that read? It says that prime factorization is unique up to ordering the factors. So let me state it precisely. So suppose n in n, and we have n equals p1 to the r1, p2 to the r2, ps to the rs equals q1 to the t1, q, let's say I used rst, maybe I'll go u, qu, t sub u, for pi, qj primes, and ri, tj not greater than or equal 0. I don't want to include 0 here because that would eliminate the factor, but rather simply greater than 0. Okay. So suppose I have two different ways of writing the prime factorization in terms of prime powers, then, oh, and suppose also, let me really nail it down. Suppose also P1 less than P2 less than PS, Q1 less than Q2. Less than QU, excuse me. Okay, suppose you have those two chains of inequalities, then U equals S and yeah, RI equals TI for every I between 1 and S, which is U. Okay, so if I have two factorizations like this, they consist of the same number of factors. Ri is Ti, oh, and of course Pi is Qi, and Ri is Ti. I almost forgot the most important part. So you have the same number of factors, the primes that occur in the factors are the same, and the numbers are the same. In other words, the factorization is completely unique. There's no choice anywhere. Everything is exactly the same. Okay. All right. So yeah, so we're gonna do an induction. So of course the way this theorem is stated is for any natural numbers. Now, in fact, I think it's a little bit cleaner to state it for any natural number 2 or greater. Kind of like I said with the prime factorization when we did the original part of this theorem. You can, yeah. In fact, I'm going to actually just do it that way because I was going to say something, but in fact, I'm going to say suppose n greater than or equal to 2. When n is 1, you have like the empty prime factorization, but I actually am not that. I'm not that interested in I mean, it's some technical notation that you can introduce, and that's fine if you want. But I'm going to just talk about the interesting case of n greater than or equal to 2. Okay, so what we're going to do is we're going to do induction, and the way that the induction is going to proceed is we're going to start with the case where n is 2, and it's actually going to be the same as for any prime number. 2 is prime, right? Obviously, and we're going to do it the same way for any prime number. So, okay, so proof is going to go by strong induction. By strong induction. Base case I'm going to do, because I think it's interesting to do it this way, n equals 2. Yeah, base case n equals 2. In fact, the same proof would work for any prime, but let's just do it this way. So one prime factorization of 2 is just 2 to the 1 and nothing else. So we have 2 is equal p1 to the r1 ps to the rs. So suppose you could break 2 down into some other prime factors. You obviously can't, right? Because any other prime is greater than or equal to 2. But let's think about it for a minute. Each p1 through ps is a prime number. And so therefore, so 2 divides, right? So let's put it this way. 2 divides p1 to the r1 ps. It's supposed to say rs. To the rs, right? But now by our previous theorem, if p divides a product, if you have a prime and it divides a product, it divides one of the members of the product, right? So it has to divide one of these prime factorizations. So 2 divides pi to the ri, or some I. And since pi to the ri is just pi times pi times pi times pi times pi, 2 has to divide the pi. And so this implies that 2 divides pi. But pi is prime. So pi is 2. If 2 divides pi, then pi is 2, right? Okay, so if one of these primes is 2 to a power, we've written 2 is 2 times something, right? So 2 is equal 2 to the ri times something else, right? And so this implies, the only way this can possibly be true, right? You can't have 2 is 2 times another natural number unless the natural number is 1. So this implies that this ri is 1 and there are no other factors. Right? I mean, that just clearly implies it. There can't be more than one prime occurring, and the power that occurs is 1, because otherwise the number would be too big. It would be 2 times another number, and that clearly can't. Okay, so that's the base case. It actually works for any prime, which is kind of why I wanted to spell it out. But yeah, okay. So now let's do the inductive. Let's do the inductive argument. So let's do the induction. So suppose true for all m less than n, where now n is some number bigger than 2. Okay. All right. So how are we going to proceed? So let's write n is, so let's do it the way I said, p1 to the up through ps3rs, which is also q1 to the t1, q u to the tu. Okay. Now these are both ordered in an increasing order. So now you look at the very smallest one. Well, it's either P1 or it's Q1, right? So maybe they're equal, maybe they're not. We don't know anything. We don't know anything yet. And so you might as well you might as well assume that P1 is less than or equal Q1, right? So either P1, Q1, or Q1 is less than or equal to P1. Let's assume, so without loss of generality, we're going to assume P1 is less than or equal to Q1. Otherwise, just change the names, right? Otherwise, just change the names in the following. Right, if I had the opposite inequality, I would just rename the p's with the q's, and I would make it this inequality. Okay, so we have p1 is less than or equal to q1. Okay, so p1 is a prime that divides n, because we've written n as p1 to some power times something, right? So okay, so p1 divides n. That implies that p1 divides q1 to the t1 dot 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 qu to the tu, right? Because that thing is n. And then arguing exactly as we did above, you have a prime dividing a power of a bunch of things. That means that this prime divides one of the things, right? So this implies that p1 divides qi to the ti for some I, which implies, in fact, that p1 divides qi. But qi is prime. And so this implies that p1 is equal to qi, right? Since qi is prime, right? Okay, but now let's look at the sizes. We have p1 less than or equal q1, and q1 is less than or equal to all qi, which is p1, right? Because the way the q's were ordered, q1 is the smallest of the q's. Okay, so this implies that I is 1 and p1 is equal to q1. Okay, p1 is q1. So this first factor in this equality, p up here, p1, is actually equal to the first factor in that q1. And so that means that I can divide n by this p1, which is also q1, and get a factorization of a smaller number, right? So now I can replace n. So now is where I use the induction. So now n divided by p1, which is n divided by q1, satisfies the following, is equal to p1 to the r1 minus 1, p to the r2, ps to the rs, which is q1 to the t1 minus 1, right? Because p1 is q1, qu to the tu. Okay, so what we have is that there's this equality between the p's and the q's with now one of the powers lowered. Okay, but n over p1 equals n over q1 is a smaller number than n. It's a natural number because that p1 divided n, it's strictly smaller than n. So by induction, we get the result. So by induction, what do we conclude? By induction, we conclude that S is U. We conclude that, right, so that's clear. We conclude that PI is QI for all I, right? We already concluded P1 was Q1. Now you see it for all the rest of them. And you conclude that R1 minus 1 is T1 minus 1, and Ri is Ti for all I. But of course, this implies that R1 is T1. So you would conclude that the two numbers, that all of the different numbers are equal that appear in the decomposition. Sorry. Implies R1 is T1. So this tells you that all of the different numbers that appear in the decomposition are the same. And so guess what? We win, and the factorization is completely unique. Okay? All right. And I think I will do a modular arithmetic lecture in a separate video. So I'm going to go ahead and sign off this one for now. All right. Thanks, guys.